Hi, everyone. Thanks for joining. I think we'll get started. I'm Dr. Destin Heilman. I'm a professor of chemistry and biochemistry at the Worcester Polytechnic Institute. I'm also a trustee of the Southborough Open Land Foundation. I'll start by thanking Sudbury Valley trustees for hosting this. I've been talking back and forth with Debbie Pullen about doing this, and I'm really glad to be here. Debbie's going to be serving as a moderator tonight for us. If you haven't heard of Sudbury Valley Trustees, this is a nonprofit organization that protects natural areas and farmland in central Massachusetts. If you're not a member, or if you are, check out their site at sudburyvalleytrustees.org for a lot of the cool programming they have going on, including this. So my talk tonight is going to be in two parts. The first part is going to have to do with light pollution and its impact on wildlife, on environments, and on humans. LED light and the advent of this new type of light, specifically LEDs that have blue in them, actually are going to have a much larger impact moving forward on light pollution in the environment. So I want to talk about that. The second part of my talk is going to have to do with reclaiming dark skies and some of the astronomy that I do, some of the outreach that I do, and to share some of my astrophotography with you and what we can do if we get out under the stars, reclaim some dark skies and have some fun and protect the environment at the same time. So I'll start with a fun fact. Maybe you didn't know this, but nighttime is supposed to be dark. We've lost a lot of our nighttime. You'd be lucky if you're outside of Boston to see a handful of stars in the sky at night. If you're in the suburbs and that urban transition, you get a few more. If you happen to be in the suburbs around Southborough, which is where I'm at, I get skies that are sort of like this. We can see maybe between 800 and 1,500 stars or so. And given the number that are out there, that's not a lot. But if we get to rural skies or exceptionally dark areas, the amount of darkness is really incredible. And what you can see in the sky is rather incredible. And so there are two perspectives to this. There's the natural resource of the sky, of the stars that we have all but blanketed with light pollution. And that's not part of our lives anymore. And it's a very important one. But there's also the impact that light pollution has on us and on the environment that's critically important. So I'm going to talk about that stuff. So I'm the faculty advisor for an astronomy club at WPI. And one of my students recently went to northern Kenya on a research project. And I told her, please look up at the sky, please take some pictures for me and send them back and I'll try to process them. So she did. And this is one of the pictures that we came up with. So this is enhanced because a camera took it, but you know, the Milky Way is quite obvious from one of the darkest places on Earth, and this is just something that we don't have in our lives anymore. That bright spot that you see, hopefully you can see my mouse, is Jupiter, which was in the southern sky at this point. Here's another view. So in 2003, you might remember there was a big northeastern blackout. And one of our astrophotography colleagues snapped a picture. This is actually another picture he'd taken, but we use it as a before. This is what the typical light pollution looks like in New England in a suburban area. And this is what it looked like during the blackout. So this is what we're missing. So we want to try to reclaim as much of that as possible and not do as much damage to the environment. So not all light is equal. Here's a picture of a high pressure sodium lamp. This is typical of what you'd find in a street light. One of the older street lights, not the newer converted ones. If we do a dark side of the moon, if you're a Pink Floyd fan, you'll get this, right? So dark side of the moon, and we put that light through a prism and we split it into its rainbow colors. I was actually really happy that they got the order of the spectrum right on the album cover. I'm not a huge Pink Floyd fan, but that was good. So this is the spectrum for a high pressure sodium lamp. And what you see is that it's got these really intense areas of these bands of light, but it's not even. It doesn't emit light in all the different colors. It sort of emits more here and less here. If we contrast this with a modern LED, it's very different. So modern LEDs emit light in all areas of the spectrum. It's a rainbow. And if we, on top of that, quantify how much light how much of each of these colors of light is coming off of this, then we get a clearer picture of what the difference is between what we've been using for decades and decades and this relatively new technology that's here now. And this is what that looks like. And the first thing that you notice right away is this blue mountain, as it's called. So in the high pressure sodium lamp, you see that one of the reasons why we observe it to be yellow or orange is because it lacks blue or green, or a lot of it in there. And so the dominant colors that come through are the reds and the yellows. The LEDs are quite different. Even though it looks like a pretty even rainbow across the colors, there's actually a lot of blue light. And this is something that is relatively new in artificial lighting. We've had lights that have a lot of blue in them, but not as readily available as LEDs. We've had sport lighting and things like this for a while, metal halide lights that have blue in them. But this is the first time that you can go to Lowe's or Home Depot and grab one of these things and put it in your house. So this has become a very, very intimate type of light for us. And it's transformative. LEDs, a typical 75 or 100 watt bulb for an incandescent can be replaced by an LED that's powered on 5 watts. And so this has tremendous capability to help the environment, and that we're not burning as much electricity and using fossil fuel and all of that stuff. But if we're not careful with these LEDs, we can actually end up doing more damage. And it's surprising because of that blue mountain. And so that's what I want to talk more about. This is why blue matters. This is why the blue light matters that's in there. Different times of the day, there's a different color of light that's naturally coming from the sun and how the sunlight is filtered through the sky. During the daytime hours, and certainly the peak daytime hours, the sunlight coming through our atmosphere is scattered, and the blue light has the most energy of all the light, the colors of light coming through. And so it's scattered the most, and that's why our sky is blue. We have a cycle. It's called our circadian rhythm. Our biochemistry is controlled to a large extent by light and the color of it. So when we're in the daytime hours, the hormones in our body are controlled. There's an area of brain, I'm going to try not to give too many big science terms, but here's one for you. There's a part of our brain called the suprachiasmatic nucleus. It's a small part of the brain, and it's actually connected to our eyeballs, but it doesn't have anything to do with us seeing. It is particularly sensitive to blue light. And when that area of the brain is activated, it suppresses hormones in your brain that control a lot of different functions in your body. And so when we have blue light entering our eyes and activating that part of the brain, it signals a waking state. We have high alertness, much more coordination. It actually controls a lot of different things related to digestion, related to immunity, and how we are functioning at a biochemical level. With the advent of light pollution, but specifically with LEDs that have a lot of blue light in them, this is what we're going to do. We're going to start adding light and adding a lot of blue light into the areas of our sleep cycle that are supposed to be very dark. And these are some effects that we know. So that one of the main hormones that this suppresses the part of the brain is melatonin. So you might be familiar with melatonin because you can go to the drugstore and you can take this stuff to help you sleep. Our body is strictly dependent on this to regulate our sleep cycle. And if there have been many studies that look into folks who are constantly bombarded by blue light. Particularly, they're looking at populations of folks like nurses that work in hospitals and night shifts where they're getting blasted by these blue LEDs all the time, that show dramatic melatonin suppression. And so this disrupts our sleep cycle at the very least. But it has dramatic effects on moods and mood disorders. It has effects on metabolism, including diabetes. It's actually been linked to a lot of different diseases because a lot of the hormones that are connected to these cycles are involved in how our body fights off different things like diseases and even cancer. And so there have been some correlations between breast cancer and other types of cancer with folks who are exposed to a lot of this blue containing light when it's supposed to be dark. So it's something we certainly want to pay attention to. And in 2016, the American Medical Association issued landmark guidance on this because the science was back building to a huge degree to say that we have to be very careful of these LEDs that emit blue light because it's causing a lot of problems for our health. And this can have a dramatic impact on human health, but also on the environment. There are dueling pieces of legislation in the Mass state legislature in the House and the Senate to address this at the state level, mainly with municipal lights, state-funded lights and highway lights and things like this. It has come out of the Telecommunications and Utilities Committee with favorable review, and it's in Ways and Means right now, so hopefully that's going to go through. You undoubtedly have a cell phone next to you or near you, or even watching this on a cell phone right now. On most cell phones or iPads or things like that, there's a night shift function now, and that's a direct representation of how a lot of the tech companies are dealing with this effect. So all of our increased screen time has our eyeballs and faces blasted with lights that's coming from these screens, and it's loaded. They're all LED screens, and they're loaded with blue light, and it's keeping people up. And the degree to which we have this exposure, especially at night, to that LED blue light is very large. So they've incorporated a night shift function. You may be familiar with it, where after, you can set the times, but after about 10 p.m. by default, it strips the blue light out of the screen, and you notice it takes a much more amber tone. So it's here. It's here. Raising awareness of this is something that I'm trying to do, but it's certainly not just humans. So from insect populations, particularly pollinators, loggerheads, red fox, spring peepers, you name it, there are animals that are affected by light pollution in general. But the advent of the blue light being part of that light pollution now en masse means that the impact on the environment is going to go up exponentially. I didn't pick a bunch of cute creatures to pander to you. I picked particular organisms where there have been lengthy studies to show that light pollution, but particularly LED light, is having an extraordinary impact on these populations. Insect populations are in decline, and this is one of the major reasons why. In addition to the biochemical effects of blue light, I mentioned that blue light is the highest in energy of all of the colors of the sunlight that's coming, or sorry, the artificial light, sunlight too, but the artificial light that's coming through. The higher the energy of the light, the more light scatter you have. So that light will bounce off of surfaces. It will increase the light trespass in doing so, which means that the amount of light that's spilling over onto other areas because it's reflecting off of everything goes up, and the amount of glare goes up. So here's a great example I like to use. Here's a college student on a college campus that's underneath a very, I'll call obnoxiously bright and blue campus lamp. Now you see him, now you don't. The student's actually still there. Can you spot him? So the student's standing right underneath the lamppost, right here. And this is a product of glare. This is when you've got such bright light, and particularly when you have a lot of scatter, so a lot of blue light, the light overwhelms your eyeballs, especially when it's coming directly into your eyes, which is glare. And it means that there are a lot of aspects of, even though the light might be shining on it in part, you won't be able to perceive because your eyeballs are overwhelmed by that. Here's another example where very bright light with a lot of glare, which means the light's not illuminating things you're looking at, it's going directly into your eyeballs, it's wasted light. If we simply cover that light up with a hand, you can see that there's someone standing in the fence. So glare is a large problem, especially with these blue LEDs. There are simple solutions to this. The easiest one is to avoid the lights that have very blue. And so there's a scale that's used for lighting, the Kelvin scale, where the higher the number, the bluer the light. The lower the number, the warmer the light. So you might have seen these if you look on the back of a light bulb at Home Depot or Lowe's. It'll have a little scale on there, and it says that, it's either a warm bulb or a cool white bulb. That's what it's referring to. And this correlated color is what can let you know how much blue light there is. And the easy solution is don't buy these ones. Try to buy the warmest light you can. And if you're like me and a lot of folks, we're really not attracted to that light that is harsh and blue and doesn't have any warmth to it. I very much prefer to have a warm light in my house, a more amber light, and it turns out it's a lot more healthy for that. And who knew? Who knew that something as innocuous and simple as light could actually be harmful to us? But technology comes around and it breeds interesting things like this. Another easy solution is that we direct the light where it needs to go. A lot of the lights I know in Southborough are of the left-hand varietal here, where they're not shielded at all. There's beautiful little acorn lights. We use them because they look good, but 20 to 30% of the light goes straight up into the sky. It's utterly wasted. And that means wasted in terms of light. It's not illuminating anything, but also wasted in terms of electricity. That's all photons that it's generating. It's not going to do anything. The light that comes off to the sides is all glare, so it's going directly into the people's eyes, and it's blinding them to stuff you'd otherwise want to illuminate. And the small amount that's left that's illuminating the objects on the ground is the only thing that's doing any good. If we can do semi-cutoff to cutoff, it's certainly much better, and we can reclaim a lot of the dark sky that we're after and stop this from impacting, shining on the woods and impacting insect populations and wildlife. The best is if we have full cutoff lights where we're simply shining the light where it's needed. If you have a floodlight in your backyard, it's to make sure that it's simply illuminating your backyard, and only when you need it to be illuminated. So there are very simple things that we can do for this. So what can you do to help? Right? Let the night be dark. Nighttime's supposed to be dark. So when you're ready to go to bed, when you're settling in and the sun's gone down, just turn off the outside lights. If you need them, certainly put them on. Try to shield the lighting so you control where it goes. Limit the exposure that you have to the blue LEDs. Best case scenario, don't have any of the blue LEDs at all. Just use less than 3000 Kelvin, which is where we really remove most of that blue mountain. Spread the word. I don't think a lot of folks are acutely aware of this issue, especially in the conservation community. It's something I'm trying to raise a lot of awareness for. I think the science has shown us that this is just as serious a problem as any other type of pollution or deforestation or anything that we're seeing. In fact, it's sort of the silent, it's more dangerous because it's the silent one that's damaging this. We're so not aware of it. It seems so innocuous that it's just not on our radar. Talk to your towns about ordinances. So one of the things that I've been involved in with the Southborough Open Land Foundation and also with the Southborough Planning Board is that I've drafted a bylaw to regulate lighting in town all across the board for municipal lighting, for street lighting, for residential lighting, to try to educate and issue culture change on the use of blue LEDs. The planning board is sponsoring that, and if we do ever have a town meeting, it's on the docket to be voted on, and so I'm very hopeful that that will be approved. But there are a lot of towns out there that have already converted over to LEDs, and that's probably a harder situation to deal with because the LEDs last forever. Well, not forever, but 15 years or more. And if the money has already been forked over to pay for those streetlights to be converted over to very white, very blue containing harsh light, that's going to be around for a while. But there are methods where the lights can be shielded post facto, and the light can be controlled. So it's if it's already there in your town, it's to talk to National Grid or talk to the town, whoever owns those lights, to try to take steps to mitigate it. There are ways, although it's not easily available, to actually put filters over those lights to block out the blue that's coming through them, and solutions like that are still coming down the pipe. So I thought I'd pause at this point because the second part of the talk, where we go into some astronomy and just reclaiming the beauty of the night sky, is a little bit different. So I'm going to switch gears, but I thought that I'd take some questions on this stuff from you. And I think Debbie's going to moderate these, or I don't know if we're going to have people ask. I'm not sure.
So if you have a question, at the bottom of your screen, you'll see a little, if you move your cursor down, you'll see it says chat. You can click on that and offer up a question. Okay, one question is, what about the bug lights, the yellow bulbs being sold as bug lights, that they're bug friendly? What's your opinion on that light?
Yeah, so there's a lot of marketing that's really coming out that's surrounding this issue, which is a good thing. And two things that I've seen are, one, these lights that are promoted to be safe for insects and this kind of stuff, and also it's one where you can control or tune the color of the light, and it actually will tune out the blue the later it gets in the day, so it actually can plug in, it knows the time and all that stuff. For the most part, you can know whether these are okay technologies to use if you know what the correlated color is. So if it's less than 3000 K, and I'd say if you're getting lower than 2700 K, then that's the safe zone. It's a safer zone for us, it's the safer zone for the environment. And so if they're advertising it to be safe for insects, they should be reporting the correlated color temperature on the bulb. And if it's less than 3,000 or 2,700 K, then it's certainly a lot better. But I'd say those would still contribute to light pollution outside. So there's not going to be any kind of light that's going to be good for the environment in terms of having it on at night, if not, but just for a temporary period of time. But if you do have to have a light on at night, if you're having a barbecue, something like that goes to the evening, then something that's less than 3,000 K is going to be fine.
So could you repeat why the blue is particularly bad?
Yeah, so insects in particular are very sensitive to blue light. Mammals in particular, because of that area of the brain, are sensitive to blue light because it suppresses melatonin. It's the main thing that it does. It suppresses pretty strongly a hormone in our brain that has a large part to do with control of a lot of different body functions. It goes beyond the sleep cycle. So it does have a large part to do with making sure that while we are asleep, that we are asleep, that we get sleepy. That we have the type of sleep that we do that's restful. It controls a lot of functions with digestion. It controls a lot of functions with overall health, because prolonged exposure to these blue lights that constantly suppresses melatonin can start to have effects on your sleep cycle chronically. And that has a lot of downstream effects. So it's mainly because we have that level of sensitivity. A different way to put it is, we have evolved under a sky that's blue. And when the sky is blue, our brain, it signals to our brain that we're supposed to be awake. And when the sky is not blue, when there's no light coming from the sky, it signals to our bodies on a biochemical level that we're supposed to be asleep. And we have disrupted that in a very large way. The fact that our brains are acutely attuned to blue light is no surprise, because the sky is blue during the day. But that's why it has the most impact. This is the first time in the history of artificial illumination that we've had such readily available lights that have blue in them. And so that's why it's a big problem.
So one last question is, they're wondering if there are any examples of ordinances that have been enacted in a town that folks can go read about.
Great question. I'm going to give my website at the end of the talk, and I have a link to another talk that I've given, and also some resources there. You can get to the legislature going through Massachusetts, but also there have been many towns that have done this. And so Gloucester is sort of like the town that spearheaded this. They are stem to stern, a dark sky city. They have ordinances that control anything over 3,000 K. And there have been a bunch of different towns all over Massachusetts and all over the country that have done this. Some are trying to control light pollution. Cambridge actually has a pretty strong ordinance, but they didn't include correlated color. So it's something that I'm hoping that they're going to do later. But it's certainly something that is happening all over the place. But we need a lot more momentum, because now the time is right, because right now is when all the towns are converting over to LEDs. And once that's done, it's going to be very difficult to go back. But I'm happy to share. I'll have my contact info, and I'm happy to share any of those resources with anyone. And I've got my bylaw as an example, and I'm happy to give it out if anybody wants to give this a go in their town. Okay. So lots of folks have seen the moon, maybe a planet or two, and then it falls off from there. So I hope that after I get done with the second part of this, that I reverse that and I'll have done my job. Astronomy redefined. Astronomy in an era at a time when we have a lot of light pollution. How do we do this? So this is my definition of astronomy now. And I emphasize the feeble human eyeballs part of it, and I'm going to illustrate that a little bit, but this is what astronomy is. You use a telescope as a light bucket. Our pupils are only about 7.5 millimeters fully dilated. And that means that the window into our eyes can only ever be opened that large. And the amount of light that can come into your eyeball to illuminate things is restricted by that. So we need a light bucket. We need a large aperture on the end of a telescope to gather more light and focus it through that little tiny window that we have. But our eyeballs are the other problem. So here's sort of eyeball 101. Your eyeball has a tissue on the back side of it here that's called the retina. And that contains two major types of cells. They're called rods and cones. The cones are the ones that are responsible for detection of bright light and detection of light in color. So we have cones that respond to red light and blue light and green light and gives us a color image. We also have rods. Rods are actually only activated in dim conditions. They are overwhelmed in bright conditions. And so they're only activated in dim conditions. They are monochromatic, so we don't perceive color hardly at all with rods. And we only get about 2200 vision with rods. So they're not very good, but they give us the slight amount of night vision that we have. Now, what's not indicated on this diagram is the name of this little feature. This is a little depression. I hope you can see my mouse. This is a little feature called the fovea. And the fovea, you'll notice, is right in back of the pupil. So anything that you look directly at, the light from that is going to be focused right on the fovea. And so the fovea has some interesting qualities to it. It's almost entirely made of cones because it's typically the bright light that's focused on this area, and it's devoid of rods. So in addition to, so now let's try to look at something, in a dark sky. We're trying to perceive something dim through a telescope, or you're trying to see more stars at night. At best, you're going to get 2200 vision. At best, you're going to get a monochromatic view. And at best, you can't look directly at it. Because if you do, you're using an area of your retina that doesn't have any rods. So our eyes are not built for astronomy, period. And that doesn't mean we don't do it. We have solutions to that. One of the solutions is we use a really big light bucket. We try to gather as much light as we can and focus it onto our eyeballs. This is Percival Lowell at the Lowell Observatory, where Pluto was discovered, looking through the Clark refractor, which is a gigantic telescope. And with the best light bucket ever, this is what a galaxy would look like, simulated through that. Now, there are some that would go, well, this is deplorably underwhelming. It's certainly not anything that I've seen, coming out of the Hubble. For avid astronomers, this sends chills up your back because you're looking at light coming directly from this galaxy that's traveled across the universe just to fall into your retinas and barely activate them so that you can see this, what we call faint fuzzy. So it depends on where you fall with this stuff. I do both visual and photographic astronomy, and so I enjoy both, but it does leave me wanting at times. And so that's why I built this. This is my light bucket. So one of the things that I do is build telescopes, and I try to show people how to do that. This is a Dobsonian telescope. It's about 7.5 feet tall, and this is my light bucket. And I'm out in Western Mass, and for the dark skies, and I have this beast with me, and this is what I use to look at the stars. But even with that, it's faint fuzzies for those objects. The planets look spectacular through that because they're a lot brighter, and we can talk about that. I'd love to have one of these. If I can live to the day I can have my own space telescope, that'll be outstanding. Because then I could take pictures like this. And so this is the Hubble Deep Field, taxpayer dollars at fine work. And so there are only two major stars in this image. There's one right here, and there's one right here. Everything else you see in this image is a galaxy. There are over 10,000 galaxies in this view. This is a 4-day exposure of an area of the sky that doesn't have a lot of stars. And it opened our eyes, literally and figuratively, to how deep and incredible and wondrous our universe is, just packed with these galaxies everywhere. So this is the kind of stuff that I get into, and here's my solution. So in the absence of a Hubble, I replace my eyeballs with a camera, and I put a light pollution filter in between the camera and the telescope to deal with the light pollution. And it's a pretty effective solution, but ironically enough, these light pollution filters are made to block out those narrow areas of light where high pressure sodium lamps or metal halide lamps emit. They are not made for LEDs, and these light pollution filters will be made useless if LED goes widespread. So there will be very little that we'll be able to do to study the sky in light polluted area. So there are three parts to sort of doing this. I thought I'd give a little bit of background into taking space pictures and just doing astronomy. But the first, of course, is the telescope, your light bucket. There's three major types of these. The refractor simply has a lens at the front that focuses the light onto a mirror. It doesn't have to have a mirror, but can go straight onto your eyeball. It usually redirects it just so you're a little bit more comfortable viewing at that angle. The reflector, we call it a Newtonian reflector because Isaac Newton was key in formulating this technology. The light comes in the front, it bounces off a mirror at the back, off of a secondary mirror, and then goes to your eye. And one of the beauties of a reflector is that you can have really big mirrors. It's easier to build mirrors than it is lenses. So you can have bigger aperture, bigger light bucket. The compound is sort of a blend of the two. It has a very thin lens at the front. It has a mirror that it bounces off. It's got a secondary, but then it sends it back this way and then up to your eye. So the reason that these were put together is because the Newtonians, the reflectors, have a lot of coma. They have sort of smearing of the stars around the edges of the mirror, and this helps to correct it so the whole field in the telescope's nice and flat. In terms of astrophotography and or visual, this is what you're looking at. So the refractors, the first type, are the most expensive by far. These are thousands of dollars if you want a really good one, but they're easy to use. You don't have to do anything to them. You don't have to tweak them or play with them. They're rock solid. You just look through them and enjoy. So they're great for astrophotography. They're great for visual. You can buy cheap ones, but you kind of get what you pay for with this stuff. The reflector is the Honda of this area. They're affordable. They last forever. They're easy to fix. And they work very well. So a reflector is a great telescope to start with, and you can, for pound, you can get a lot of aperture for your money. A compound is very popular because you know, it's one of these telescopes that's really short and portable and that kind of stuff, but it turns out that they are not very easy to use. They're finicky, they have to be adjusted all the time. They're sort of in the middle of price point. So I like refractors for astrophotography. The mount, you have to have the telescope sitting on something. And here's another fun fact. I don't know if you know this or not. The Earth rotates, and that's kind of a problem for doing astronomy, but especially if you're trying to take pictures. Everything would end up smeared. So you've got to have a mount that moves with the sky, moves with the Earth. Here's the Clark refractor again from Percival's view. And so that thing is mounted on a gigantic mount. And you'll see that it moves in a couple of different directions. And the big circle that you see right here, that is the right ascension axis, and that helps to move along with the Earth's rotation. And so you gotta have a good mount. You gotta have an accurate mount in order to take long exposure pictures. And then of course the camera. You can take pictures with one of these. And I've been able to get pretty decent pictures. All these pictures are taken with a cell phone. I thought I'd highlight where Apollo 11 landed, since we're going through these great anniversaries of the Apollo program. Jupiter, Saturn, and so you can do this with a cell phone. I don't want to mislead you. There's a little bit of post-processing you have to do to the images to get them to look like this, but there's free software to do that. An upgrade to that, though, to get you a large upgrade, is a DSLR. You can strap these right to the telescope and snap some pictures, or you can buy a dedicated astrophotography camera. These are scientific grade cameras that have lots of different filters in them that not only block out the light pollution, but can allow you to actually select different kinds of things you want to take pictures of. This is where the chemist in me comes out, where I can actually filter out all the light except that coming through from hydrogen or from sulfur or from oxygen, and do some interesting photography, just like the Hubble takes pictures. And so we can do this now at the amateur level. This is my wife's favorite part, because I get to talk about all the different rigs that I have and all the money that I've spent on these things. But because I have 3 primary rigs, one of the reasons is, and I've tried to argue this to my wife, you can't zoom on a telescope. So your image scale is controlled by the size of telescope you have. And interestingly enough, the smaller the telescope, typically the shorter the focal length. This means the wider area of sky you get. So, you know, you got to make the argument that you need lots of telescopes. You can take different image scales, right? At least that's what mine was anyway. I built an observatory because it's kind of a pain setting this up and tearing it down all the time. So it's a little mini observatory. I wanted to make it, hide in plain sight as a little woodshed, but the roof slides off and there's a rig underneath. So it takes me 45 seconds to get the system going and snapping pictures. And in New England, especially when you never know when you're going to get a clear sky, it's nice to be able to set up that quickly. So the results. So after 6 hours or so, so I take long exposures. I don't take one 6-hour exposure. We take what's called subs. So you take 5 or 10 minute exposures, and then you smush them all together into a long exposure photograph. After about 6 hours pointed at the Andromeda galaxy, this is what you get, right? Money well spent? No, not exactly. So there is a lot of processing that has to happen after the photos are taken to suppress the noise in the image, to draw out the detail. And there's just as much of a learning curve on the photography side as there is on the processing side. So I'm gonna take you through just sort of what one of my images looks like from start to finish very quickly. The first thing you would do is stretch. And I hope Keynote has not locked up again. It's possible that it did. There we go. Okay, so you stretch it. Now we're starting to see a little bit of the galaxy coming out. You suppress the background. If those of you that have done photo editing before, you might know that you adjust the black point of the image and the white point of the image. You adjust the midtones and the darks, and you start to bring out these images. So you start to really try to bring out the target and to accentuate it and not let the stars completely blow out. So there's some suppression of the stars a bit when you do the processing. There's a lot of color adjustment that has to be done because oftentimes the light pollution produces a lot of greens in your images. Enhancing different features, dust lanes and galaxies, drawing out those features. And then there's a point at which you get where these images and the Hubble images that you see, these are nothing of which our eyeballs would ever perceive. You can make images that might look like they would if you were floating in space, but the truth of it is these objects are exceptionally dim. And even if you were floating in space this close to this galaxy, it would never look this bright. So there is some artistic license with this. We'd like to see the objects and be inspired by them. So this is sort of what the image ends up looking like. And so there's a lot of processing that goes into it. Just to zoom in and show you a little close-up, you can get a lot of detail in here, and it's fun. One of my favorite things to do when I process images like this is just spend a lot of time zooming and panning around to find all little Easter eggs and things that I like to see. So where do I point the telescope, and where would you point your telescope? So I'll give my Frisbee analogy for this. So we live on a big Frisbee. We are in a spiral galaxy. You can think of it as a big disc or a dinner plate, like a Frisbee. This is about where we live in our galaxy. So you are here. There are 2 directions generally that we can look when we live in a Frisbee. So remember that we're inside the Frisbee. We live in that disc. We can look up and out or down and out of the plane of that Frisbee. And in that case, we're going to see deep space. We're going to see everything that's not in our galaxy. Maybe we'll see some foreground stars that are there, but we're looking through the thinnest area of our galaxy right out into deep space. Or we can look in the plane of the Frisbee. And that's looking into our own galaxy where we can see a lot of close-up objects. And so there are really two seasons, so to speak, of astronomy. We call it galaxy season and nebula season. The Milky Way, our own galaxy, is really up in the sky and prominent at night during the summer. And that's when we see a lot of the things inside of our own galaxy. And then in the very early spring and through the late parts of the winter, that's where the Milky Way is not within our view easily at night. And we see up and out of the Frisbee and we see deep space. And so there's galaxy hunting season and there's nebula season. So to go back to that picture that one of my students took, this band of stars that you see going down through is, of course, the Milky Way. That's our own galaxy. But I hope you get a little bit better appreciation of the Frisbee. This is our galactic bulge. That's where the core of our galaxy is. It's in Sagittarius in the south. And if we point our telescopes along this band, we're looking into the Frisbee. And that's where we'd be able to see nebulae that exist in there and close objects. If we point out and over to these areas, that's where we're pointing into deep space.
and you can see other galaxies and things like that. So 2 major places that you can point. So quick sky tour, I suppose. First, we'll start with deep space. So this is looking up and out of the Frisbee, or down and out of the Frisbee. And so these are some of the deep space pictures that I've taken. A lot of these galaxies don't have names. They have catalog names and numbers, but some of them are just really beautiful to process. They have such great features. Sometimes you get more than one. Some of the galaxies have only a single spiral arm that spirals all the way around. You get these ones that have what we call a tidal tail, which is because it's interacting with another galaxy and they're starting to shed stars into space as their gravity starts to pull on each other. This one's called the Leo trio because it's right under the lion's belly, the constellation Leo. But these galaxies are interacting with one another. You can see this one looks like a Dali painting. It's sort of smeared and like that, and that's because it's gravitationally interacting with the others. We call this one the hamburger. When you look at it through a telescope, visually, it kind of looks like 2 buns and a piece of meat between them. I guess that's where that comes from. This one's called M106. It doesn't really have a name, but it's one of my favorites to take a picture of. I don't know if you can see it very well, but there's a little tiny red feature that's popping up out of this galaxy right there. I'll take my mouse away from that. Hopefully the video feed is good enough for you to see that. That is a hydrogen jet. This, I don't know if you might have seen news articles in the past year or so where scientists were actually able to take the first picture of the event horizon of a black hole. It wasn't this galaxy, but this galaxy does have a supermassive black hole at its center, and it's actually tilted by about 30 degrees. And that means that when it blows off radiation, its polar jets, they're called, its poles, it's pushing hydrogen in the galaxy up and out of the galactic plane, and you can actually see that. And so that's one of the things that I got giddy about. I took this picture because I wanted to try to see that feature, and so I was very happy that I was able to see that. So learning a lot about these objects is part of why I love doing it, looking them up and learning about them, picking a new target. This one's called the Whirlpool Galaxy. This one's actually near the Big Dipper. It's in Ursa Major. It's actually 2 galaxies that are colliding with each other. So the larger one is being eaten by, the smaller one is being eaten by the larger one. And when their gravity interacts with each other, the gases get crushed and you get all of this starburst of new formation. And that's why the spiral arms of this galaxy look so blue. Young stars are very blue. They're very white hot stars. Older stars are orange and red. This is the Pinwheel Galaxy, and it's also being gravitationally interacted, and so it's got a lot of blue and magenta in its star clusters. It's a very difficult one to see visually because it's very dim. These 2 are also in Ursa Major in the Big Dipper. So this is M81 and M82. They're also interacting with each other. You can see that because of all the blue that's in each of their outer galactic parts. And there's these beautiful dust lanes in M81. But M82 is sort of the jewel because it has been crushed so much by M81's gravity that it's been made into what we call a starburst galaxy. There's so much star formation going on, and the gases have been pushed so far to the interior of the galaxy that the black hole at the center of the galaxy is spinning up and spewing out the hydrogen gas up and out of the galaxy. So all this red that you see flying out into space is the hydrogen just being thrown out of the galaxy. It's a very dramatic aspect of some galaxies. So here's another galaxy that's in our local group. This is the Triangulum Galaxy because that's the constellation it's in, and it's a lot bigger because it's a lot closer to us. So I didn't mention it, but most of the galaxies that I just showed are anywhere from 12 to 200 million light years away. Distances are too big in space to measure by feet and miles and that kind of stuff. And so we measure them in light years, which is not a time, it's a distance. It's the distance that light would travel in 1 year. Light travels at 670 million miles per hour, give or take. And so that's the distance that light would travel at that speed in 1 year. So when we say that a galaxy is 20 million light years away, we're saying that it takes the light moving 670 million miles per hour 20 million years to reach us. That's how far away these are. So that's one of the things that makes astronomers so giddy when we're looking at these, because we imagine that the light left that galaxy 20 million years ago and traveled through space that long just to land on my retina so that I could see it. It also means that anytime you look up into the sky, whether it be the moon or a distant galaxy, you're looking at a history book. Looking at this galaxy right now, which I think is about 3 million light years away, it's relatively close. This is not what this galaxy looks like now. This is what the galaxy looked like 3 million years ago. One of the reasons that I like to end the galaxy stuff on this is because you see that this whole galaxy is peppered with these little red nodules everywhere. This galaxy is close enough that we can actually start to see features of its nebula, its nebulae, the large clouds of gases that form stars. This little jewel that's right up here in this area of the galaxy is the largest known nebula in any galaxy that we've seen, including our own. It is absolutely gargantuan, and that white spot at the middle is heavy amounts of star formation. So we're going to transition over now to things in the Frisbee, and I want you to imagine that now we would be in a galaxy like this, looking close up at nebula like this. So we'll transition to looking into the Frisbee, and you'll see that things change. We start to see totally different things. And so this is something called a globular cluster. This is a cluster that's in the near the Hercules constellation in our own galaxy. It's about, these are about 50 to 100,000 light years away, so much, much closer. And these contain anywhere from hundreds of thousands to millions of stars in a giant compact ball. We do not understand where these come from. Every major galaxy has 100 of these, maybe 200. They might be vestiges of the cores of galaxies that have been gobbled up by bigger ones. We're just not sure. And that's one of the puzzling aspects of looking at these things, but they're beautiful and they're bright and wonderful things to look at in a telescope. There are open clusters. So as opposed to a globular cluster, there are open clusters. These are loosely packed groups of stars. If anybody drives a Subaru, you might be familiar with this cluster because it's where their symbol comes from. This is the Pleiades. Pleiades is an open cluster that's a wintertime cluster of stars. It's called the Seven Sisters, colloquially, historically. And the Japanese name for the Pleiades is Subaru. So that's what they have on their symbol. They undercut the number of stars. But one of the things that, if you take a long exposure of the Pleiades, you see these paintbrush-like strokes around the stars. And that's because this whole star cluster en masse is plowing through the dust in our galaxy. And as it does, it's just shining its light on the dust so that we can see it. So it's sort of illuminating what otherwise would be darkness to us, but there's dust there. And as these stars pass through, they shine like little light bulbs on it so that we can see it. This is the exploded guts of a dead star. So this is a supernova remnant. So when stars fuse all of their fuel, hydrogen to helium and then to larger elements, they eventually die. And if they're big enough, they'll explode in a supernova explosion and just blow all that material out. And so it forms these features in space where we see hydrogen and oxygen spewing around. Most of the pictures I'm showing you now are taken with a DSLR camera. So you're seeing these in RGB. Here's another one. This is a wintertime constellation. This is the Great Orion Nebula. And if you go out and, most of you, if not everybody, can spot Orion in the sky. It's one of the most prominent constellations. And the sword hanging off of Orion's belt is this nebula. It's actually not a star. So you can see it with the naked eye. A small one. It's a spectacular view. It doesn't look like this, but it's one of the most active areas of star formation in our galaxy. And it's right next door. It's only, I think, 1,500 light years away or so. And then right in the same region is the Horsehead Nebula, which you may have heard of. And so this is why we call it the Horsehead, right? There's this big plume of dust that comes up and looks like a horsey. But This one's in Orion as well. This star right here and this one here are two of the stars in Orion's belt. This is El Nitak and El Ilam. Those are the left two stars in Orion's belt from our view. So this Horsehead Nebula is right around them. It's impossibly dim, though. You can't see it with a telescope unless you have a special filter. So if you opt for an even better sensor, if we move away from a DSLR, which my wife was very happy that I did, onto a dedicated astrophotography camera, then you get not only a much more sensitive sensor, but you also get the ability to put these filters in front of it and separate out the different elements and colors. And it sort of ups the game for the type of photography that you can do. So the way that this works is you change those filters and you take, for every target, 3 pictures. So it's a lot more work to do this. So this represents, and it's monochromatic. These are black and white images with different filters in front. As you can see, there's a different pattern in the images because one of these is taking pictures of sulfur, the other one's pictures of hydrogen, and then pictures of oxygen. This is precisely how the Hubble Space Telescope takes pictures. And then what we do is we assign them color channels. And this can be done arbitrarily. It's sort of a misnomer to call it false color, but we assign them channels and then we combine them and we get something that looks like this. So this is the Rosette Nebula. And you get a lot more features, you get a lot more detail with a better camera, and you get this spatial distribution of the different gases that are there. One of the things that's always interesting is that the heavier elements, they don't move as much. They have more mass. And so the lighter stuff, as these stars, right, these nebula are they're cradles of star birth. As these stars in the center are born, they start emitting radiation out and they push all the gases outward. And the oxygen gas, which is heavier, and in this case blue, is not pushed out as far as the hydrogen, which is way out toward the edge, and that's red. So not only can we get pictures of the stuff, but we can study spatially where things are at. We can look at the elemental compositions of the nebulae. So I like to do some science with these pictures too. So here's one that's called the Cygnus Wall in the Great Swan, the Northern Cross. Taken in the same way, very dusty in that area. This is another supernova remnant. This one's called the Jellyfish Nebula. So this is the exploded guts of another star. This one is called Setterblad 214. It doesn't have a really good name to it, but I like this one because the stars that have been born in the core of this, you see the same pattern. The oxygen is being blown out, but then further out is the hydrogen. But I like this one to illustrate because you start to see these features here, these pillars of gas, then they're all pointing toward the inside of the nebula. The reason this happens is because this is where the gas is really, really dense. At the tips of these pillars are stars that are in the process of being born. There are protostars in those tips. And because the gas is so dense there, when the radiation from the stars that are already born starts to blow the gases outward, these ones don't move as much. So they protect the gases around them and behind them. So they form these pillars. And so it's great because it means that you can look at a picture like this and you can know where the stars are going to be born. Here's an extreme example of that. This is a close-up of one of these pillars. It's called the Elephant Trunk Nebula. And you can even see some of the early activity from the star that's about to be born in the head of this thing. And when it's born, it will blow off all the gas around it and expose itself to the rest of the nebula. It's called the elephant trunk because the Hubble took a picture of this sideways in different colors, and they thought it looked like an elephant's trunk. This one's called the Heart Nebula. It's in Cassiopeia. And same thing, it's got lots of stars that are being born in the middle, and you get these pillory sort of projections that come out. And in Cassiopeia, there's a nebula that's right next to the heart. It's also very prominent, so it's called the Soul. So there's the Heart and the Soul Nebula right next to each other. And this one, the Soul Nebula is neat because it's actually two. There's two star-forming regions, two bowls. And same thing, you get the pillars, and we know where the stars are going to be born in there. This one's called the Cave Nebula. It's another dusty nebula. This one is called the Flaming Star Nebula. It's in Auriga. constellation. And it's just a very dramatic one. There's just lots of hydrogen gas, but there's also some dusty filaments that sit near this. They're called reflection nebula that sits on top. When I process these images, oftentimes, if you push the image too hard, the stars sort of become way too bright and they take over the image. And so one of the processing techniques that I like to use is called tone mapping, where when you're processing it, you remove the stars, you take them out, and you process the nebula by itself, and then you put the stars back on. And it allows you to have a lot more control. But sometimes when I take the stars away, I don't like to put them back. So this is an example of one without the stars. And you really get a sense of the nebula itself, all the turbulent movements of the gas and this kind of stuff. I chose to keep the main star in there because it sort of looks like it's illuminating the nebula. So this is more artistic license on my part, but I like to do this in some of the images that look good with it. This one's called the Wizard Nebula. If you turn your head at like a severe 90-degree angle to the left, you'll see the wizard's hat and his nose and his eyeball. And then here his hands and his feet. And then his cloak is back here. It's one of those things where once you see it, you can't unsee it. But this was another image that I did where I liked it very much when I took the stars out. So I sometimes, not all the images look great when you do that, but here's just a couple of examples that look good. This one's called the Pelican Nebula, because when you zoom out and you take a wide scale picture of it, actually looks like the shape of a pelican. But this one I thought also looked nice without the stars. Here are these pillars, right? And interestingly, if you look on the tip of this one, there's a little tiny white thread that's going left to right on it. That's called a Herbig-Haro body. It's the polar jets of a newborn star that's spinning up, blowing out the gases on opposite sides. And that tells you that there is a star that is just about to break out of the end of that pillar. So this is my plug for you to go outside and look up, get started, go to a dark place, better yet, make your place dark, and encourage your neighbors to make it dark and your administrators to make it dark. Go outside, look up. There's so much out there. Grab some binoculars and look up. Binoculars are a fantastic way to look at the sky. One of the best ways to look at the Pleiades cluster is through binoculars. Your library undoubtedly has learner telescopes, or learner and loaner telescopes. So grab one of those, go outside and look up. They usually have instructions, they're easy to use. Buy your own telescope, give the library back theirs, and do the same. Try snapping pictures with your cell phone. Do something bright, the moon, planets, things like that. Get hooked, and then you got to talk to your family about all the money that you're going to spend on this stuff. For a couple of $100, maybe $300-400 if you push it a little bit, you can buy a telescope like this from Celestron, one of the primary companies. I'm not plugging them at all. I'm not but it's one of the companies that sell these, but their prices are right. This is a small reflecting telescope, and it's on a computerized mount that once you align it to the sky, it will automatically move to objects and let you look at them. And so it's a great starter telescope, this style, and it's tech that wasn't available to us just a few short years ago. They've been able to cram all the computing power and databases into these things necessary to do this, and they're great little telescopes to start with. It used to be that when you buy a telescope, it's really frustrating to find things in the sky, and these help you to find those. So here's what's in the sky now that you can go outside and look at. I'm not sure what the sky looks like around you right now, but I'd strongly encourage you to get out there tonight if you can. So in the next month, I think this is my planetarium program on the 5th of May, so coming up close on Cinco de Mayo. If you are an early riser, or if you're really itching to get out and look at this stuff, if you get up at around 5 in the morning and look to the southeast, this is what you're going to see. You're going to see Mars and Saturn and Jupiter. These planets are typically up at some point every year, but this is going to be a beautiful juxtaposition of them in the sky. They're super bright. They're often almost always mistaken for stars, but they're not. They're planets, and they're unmistakably bright, and you can't miss them. and Mars has a characteristic red tinge to it. They're spectacular if you look at them just with your eyeballs. They're even better if you look at them with a telescope. Even the smallest of telescopes with Jupiter, in fact, even with good binoculars, you can see the Galilean moons around Jupiter. You can see the rings of Saturn. So get out and look at these things. Amazingly enough, I actually had to look it up, but the Lyrid meteor shower is peaking tonight. So if you happen to have a clear sky, get out tonight and look up. If you face the northeast, you're going to see the brightest star in the sky right now. It's Vega, and that's in the constellation Lyra. The radiant, which is where the area of the sky where all the meteors are coming from, is just next to Vega. And if you point your face that way, it's best if you just get into a reclining chair, put a blanket down. Of course, it's freezing outside, but bundle up and just wait, and you'll see these amazing fireballs coming through the sky. These are all cometary debris. So it's the Earth passing through the tail of a comet that passed through ages ago. As we do that, the little micrometeorites fly through our atmosphere and burn up. So it's a great, great, great show. So if you want to know more, my website is stellarsolace.com. It's got a lot of information on how I take pictures and how you can take pictures, but also my gallery and a lot of my outreach. And so there's some information on LED lights and blue lighting and the health concerns about them and other talk that I gave. I have a Facebook page where I post images every once in a while. Darksky.org is the International Dark Sky Association's website, and you can go there for a lot more information on combating light pollution and things like that. Spotthestation.nasa.gov is one of our favorites. This is how you know where the International Space Station is. Every 90 minutes, it circles the Earth, and a lot of those passes are, it's illuminated by the sun. So just after the sun goes down, it's illuminating its solar panels, and you can see this thing streaming across the sky. Most folks don't know what it is, but it's really amazing to watch because it passes the sky in about 4 minutes, and you can wave to the astronauts that are up there. So try that out. I do a lot of astronomy at the Chestnut Hill Farms, where I run a lot of outreach programs. We started a natural sciences club in Southborough. You're welcome to join. You don't have to be from Southborough to do that. And like I said, you can contact me through my website, stellarsolace.com. There's a contact form if you want more info or anything about this. I'm absolutely happy. I'd be happy and thrilled to get everyone involved. So I'm happy to take any more questions that you have. Thanks so much for having me in and listening to all this stuff.
So we do have some more questions. One question is, how do they know how many light years away a particular star is?
It's an excellent question. There are a couple of different methods that's used for this. The primary one is called redshift. So Edwin Hubble, along with a lot of other great scientists, figured out in the 1920s that the universe is expanding. It's not only expanding, it's accelerating. And as it does that, you sort of get a Doppler effect with light. So you know that Doppler effect you get when a car goes by. It's sort of that train goes by. It's sort of and the frequency of the sound changes. The same thing happens with light. And that means that the color changes. And so we can actually tell how fast a galaxy is receding by its redshift. And so that's part of the puzzle of how we put together how distant they are. And then you got to have more information. So Edwin Hubble, along with a amazing scientist that came out of the Harvard College Observatory, Henrietta Leavitt, discovered something called Cepheid variable stars. And these are stars that have very reproducible brightness, regardless of where they're at. And Hubble found one of those in the Andromeda galaxy. And when he did, it dramatically expanded the size of what we knew the universe to be. They thought that the Andromeda galaxy was actually a nebula, and that the entirety of the universe was only a few 100,000 light years across. And he showed that it was millions of light years away, and that was only one. So it's a combination of using different things. Variable stars, when type 1a supernova have a very reproducible brightness. So it's sort of like, if you know how bright something is, and you can quantify how bright it looks to you, and you know how bright it's supposed to be, then the order of dimness that it is lower than that is directly correlated to the distance away. So you can tell sort of with a combination of the brightness of these special stars and redshift, how far away they are. It's very difficult though. Scientists are also trying to use parallax to do this. So the easiest way to demonstrate parallax is I wish I could see everybody do this, but put your finger up close to your face like this. Don't trust, nobody's watching, I can't see you. Close one eye and then close the other eye and open that. And you notice that your finger moves back and forth. That's called parallax. It's the observation that something looks like it's in a different place based on the angle that you're viewing it. So what scientists can also do is we can take a picture of the sky, a galaxy or something, and then wait 6 months until the Earth is on the opposite side of the sun. And just like your eyeballs being in two different places, we take another picture of it, and relative to the things in the background, it will shift a little bit. And based on the degree of shift, we can also tell how far away it is. But that only works for things that are closer. So that's a few of the ways that we can do that. Excellent question.
Here's an interesting question. So what are your thoughts on Starlink and other satellite constellations going up? Is space junk in general getting in the way of astronomy?
It probably doesn't surprise you to find out that I have very strong feelings about this stuff. I am all for disseminating internet access to the world. I am certainly not for doing it the way that Elon Musk is trying to do this and some other companies. So for those of you that don't know, Starlink is very small clusters of satellites that are being put up by, it's SpaceX, I guess, into orbit to try to provide orbital-based satellite internet all over the world. And it's a great idea in principle because you can give people in extreme rural areas, in areas you'd never be able to get high-speed internet to, access to the world. But it's going to require tens of thousands of these satellites to be put into orbit. The FCC has already approved tens of thousands of these satellites to be put into orbit, and SpaceX is throwing them up into orbit as fast as they can. They are bright, they are always there, and they are going to have a tremendous impact on astronomy at the amateur level and at the professional level. It is very typical when I take pictures of things in certain areas of the sky for me to get streaks of satellites coming through. And there are ways to subtract those from your images. If you Google Skylink and astronomy, you'll get dozens of pictures that pop up of professional telescopes that have hundreds of streaks through these as these things go by. Imagine the Earth surrounded in a webwork of these satellites at regular interspersed distribution. There will not be a place in our sky that we can point a telescope and take a picture without getting hundreds of streaks through it. It is going to be a disaster for astronomy. And they're trying to do things like painting the bottom of these things black to mitigate the reflectivity of them. And so far it hasn't worked at all. So it is troublesome, and it is absolutely an area where technology has leapt forward too fast. And I have very strong feelings on it. So I'll keep it at that. But yeah, it's a big concern.
So one last question. Our participants are wondering if you have any recommendations for good places to stargaze with less light pollution in our area, in the Metro West Boston area.
Wallback Farm. It's any place that you go that's going to be away from the big city. So you got to get away from Boston. You got to get away from Worcester. Is going to be oodles darker. I'm in Southborough, so it's midway between Worcester and Boston, and it's reasonably dark. I would say that in that graphic that I showed you with the urban sky, the suburban border, and then the suburban sky, it's firmly in that third category. So Southborough is reasonably dark. I mean, it's nothing compared to a dark sky site. But anything you can do to get yourself away from lights. So the Chestnut Hill Farm in Southborough is where I like to go. It's not just because it's in Southborough, it's also because it gives you a 360 view of the sky. But also there's a lot of obstructing trees that block lights from houses that are nearby. And so a lot of it can be mitigated if you simply block the light from coming into your eyes. You'll be able to see more. You can't get away from the light domes from the cities. There are some really dark places in Massachusetts. In Western Mass, there are some dark places. But you got to travel. If you have interest and ability, you can go to the Atacama Desert in Chile. It's one of the darkest places that are around. And that's why there are a lot of professional telescopes there. Anywhere where you see professional telescopes, go there. But you have to travel a little bit. But it is well worth it. If I could launch another poll right now, I would ask how many of you have been to the Grand Canyon and you didn't look up? It's probably a lot. And places like that, we oftentimes travel, but we don't think to do that. And it's forgivable because we don't have that here. You can't live outside of Boston and look up and see anything worth it. And so we're simply not used to it. I have some colleagues that I work with that have come from places, very dark skies, from Brazil and from places in Africa, that actually tell me that they experience anxiety when they come to places like this where you can't see the stars because they feel claustrophobic. They feel as if they don't have that window, that there's this veil over top of them. And it's interesting to think about what we've lost. We might be able to get it back if we take some good steps.
Thank you. So I want to thank everyone. I'm going to leave Destin's picture on the screen, but I want to thank everyone for joining us tonight. It was really a lovely and refreshing evening. And I think you've given me a lot to think about and a lot of interesting things to explore. And those pictures are just gorgeous. So thank you so much for your time. And thank you everyone for being with us this evening. And do stay well and take care. And we hope to see you on the trails at some point soon.